This conference will now be recorded.
Okay, good morning, students. Let me start the class. In today's class, we are going to discuss about how we can calculate the inductance based on the flux in a conductor. So in last class, we discussed about how the resistance and inductance we can calculate in the conductor. And now in this class, we are going to derive how the inductance should be varying due to internal flux and external flux. So that is the thing we are going to do. So this is the very important derivation in our section exam. So all of you keep a notebook in front of you and just follow my class and note out the equations and you can know that how the derivation will come. So let me start the class. So this is the topic today we are going to discuss about inductance of a conductor due to internal flux and external flux. See, if you see that the resistance and inductance, what are the parameters will affected on the resistance of the conductor? What are the parameters will be affected on the resistance of a conductor? Suresh, Suresh, are you there? Right. See, note down this derivation. After that, you have to submit that what you wrote that in this class. So then only you can get the attendance. Otherwise, you won't get. So let me start the topic. So this is the inductance of a conductor and due to internal flux. So in this class, we are going to derive the equations that is inductance for internal resistance as well as external resistance. Why? Because the inductance should be vary with respect to the cross-sectional area of the conductor. Now let me consider that conductor that is ACSR, that is aluminum conductor with steel reinforcement. In that so this is the part, it is made up of a steel and the outer surface is made up of aluminum. It means that both are different conductors and both have the different capabilities of current flowing and it will generate the different flux. That's why we are finding that separately for internal flux as well as external flux. Now starting, let me consider that long and straight line conductor with radius r. So this is the point. This is the distance from center point to outer surface, and x is the radius from center point to the material is having that silicon. So from center to material surface of the steel material, and r is the radius of the center point to outer surface of the conductor. So these are the parameters, and I is a current flowing through it. So how we can calculate the inductance means when the current is flowing through the conductor, there is a flux will be generated. Due to the flux, the inductance will we can calculate that. and so this here the magnetic field will be established due to the current. Now this is the different parameters and the radius we obtain here, and the entire derivation is depends on that two parameters. One is maximum flux density, flux density, and flux intensity, magnetic field intensity. What is the relation between these two? What is the relation between magnetic flux density and magnetic flux intensity?
B equal to mu naught into H.
B equals to
Mu naught into H.
right. So B is equals to nu H. Actually, the nu can be written as nu naught into nu R. So the relation is B equals to nu H. So this is the relation between magnetic field density and magnetic field intensity. Here nu can be written as nu is equals to nu naught into nu R. Right? This is the value of nu. Based on these two parameters, we are going to derive that inductance of a long and straight line conductor. That is internal flux. So just note down the derivations what we discussed. Why? Because then only you can understand that what is the upcoming step. So when the current is flow through the conductor, the mmf in ampere turns around any closed path is equal to the current. It means that the mmf, the magnetic motive force, is depends on that how much of current is flowing through the closed path, and this integrations indicate that this intensity should be generated in the closed path. So that is the notation of this closed loop interface. So this is the mmf will be generated when the current is flowing through the any closed path. So here we are finding the internal flux, right? So internal part is closed. So there is a mmf will be generated due to the current, and it is denoted by equation 1. And here H is a magnetic field intensity, and its unit is ampere turn per meter. It means that how much of current is flowing through the different meters, that that value we can get that here. Now let a magnetic field intensity at a point X. So see here, this is our conductor and it is our internal part. So let me consider ACSR. I already told that the internal part is made up of steel and outer is aluminum. Now we are finding the only internal flux, right? So that is only belongs to the internal part. From center to internal part surface, the radius is X. From center to outer surface, the radius is R. So we are finding the internal flux, right? So that's why we are deals with only point X. So from center to this is the X point we are going to. So the magnetic field intensity at a point X meters from the center of the conductor. So how it means, see. So this is the center. This is the center point, and we have to find the magnetic, that is intensity, up to this point. So here the obtaining of mmf is denoted by Hx, and this is the constant at all points as field is symmetrical. Why? Because there is no changes occur in the field. That's why we are getting the constant Hx in this conductor. Now the integration of ds around the closed path, circular path is 2 pi x. So what is the formula for circumference? 2 pi r, right? See, if you considering outer surface, if you consider the outer surface, the circumference of the outer surface circle is 2 pi r. But we are considering the internal part, right? So the circumference of the internal part is 2 pi x. So that's why. So this is the closed loop. The integration of ds around the closed circular path is 2 pi. It means that the inner circumference circle is denoted by closed integration of ds is equal to 2 pi x. Now, if you see this, if you observe the equation 1 and equation 2, how we can solve this equation while considering 1 and 2. So instead of integration ds, so let's consider it is a comes to outside by. Why? Because it is a constant value. Instead of integration of ds, you can write 2 pi x. So finally we'll get hx into 2 pi x equals to I. So here 2 pi x is a circumference of the internal circuit. So that is the center point to the point x, that is the radius x. So here we can write as 2 pi x. If you want to find the total circumference, we will get 2 pi r. So from these two equations, what you will get means, so this is the equation, final equation you will get after solving the 1 and 2. So instead of integral ds, we are placing the 2 pi x. From this, hs is equal to ix 2 pi x. So one parameter is over. So I already said this entire equation is depends on two parameters. One is magnetic field density and magnetic field intensity. So now we apply that magnetic field intensity at point x, that is given by hs is equal to ix divided by 2 pi x. So this is the current at point x and this is the circumference until at point x. So here xs is a constant. So just mention here this is equation 3. Already two equation is over. One is equation that is mmf is equal to I, and second equation is circumference of the internal circle, and by using equation 1 and equation 2 we obtain the equation 3. Have you all noted these equations? Then only you can understand. Note చేసుకుంటున్నాం అండి ఇది derivation.
Okay, sir.
Right. See, if you have any doubts in between this, just clarify now itself. Why? Because if you understand this derivation, then you can proceed that upcoming derivation. Then only you can understand. Otherwise, you can't able to understand the derivations. So it is the most important derivation. Definitely, you will get. So already one question is over. That is the type of conductors. You will get one question from the type of conductors, the bundle conductors and skin effect. So that is the one part. And second part is calculation of inductance. So one of the question most important you will get from the inductance calculations. So that's why listen carefully. So now three equations are we obtained. Now we'll go first third one. Now as the current density is uniform at the both inside and outside. Suppose why this term is indicated means based on the density of the conductor, the current allowing will be more. Suppose if you take any vessel, so based on the capacity you can fill the water. If the capacity is exceeded, what will happen? The water will flow on outside. So same thing, the amount of density will allows the flow of current. Here I am considering that same current is flowing through the entire conductor. That's why I am equating that internal density and external density, that is ix divided by pi x square. So it means that how much of area is having, that much of current should be flowing. So the current of flowing should be depends on the area. So what is the area of circle? Pi r square, right? So this is the internal part. So that's why I mentioned here x. It is outer side. So both are equal. Why? Because the current is flowing through the entire conductor is same. So that's why I am considering here. Why? Because that is the reason we are considering h is equals to constant. So the density can be written as like this: ix divided by pi x square equals to I divided by pi r square. So this is the density for internal side, and this is the density from external side. If you solve this equation, both sides pi will get cancelled and ix. So our main concentration on x point. So that's why we are considering that ix here. So is equals to x square divided by r square into I. So let represent it is equation 4. Now substitute ix, that is the substitute equation 4 in equation 3. So what is our equation 3? So this is xs is equals to ix divided by 2 pi x. hx is equals to ix divided by 2 pi x. So this is our equation 3. Now substitute equation 4 in 3. Instead of ix, substitute r square divided by x square into I. So what you will get? xs is equals to 1 by 2 pi x, then x square by r square I. So finally 1x get cancelled. X divided by 2 pi r square into I, and its units is ampere turn meter. So this is the final equation for the magnetic field intensity at point x when the flow of current I with respect to the circumference. So hx is equals to x divided by 2 pi r square into I ampere turn meter. So this is the final equation of h. Now we have to find the b value. If you already know the h value, how we can calculate b? By using this equation. B is equals to nu into h. So let me see how we can calculate that. So this is the already we found that equation Hx, right? Now by using this Hs equation, we have to find that magnetic flux density, that is flux density Bx. So there is a relation between this flux density and flux intensity. Bx is equal to nu into Hx. So already we have the Hx value, right? Just substitute here. Bx is equal to nu into x divided by 2 pi r square into I. So what is, so the flux density having the two units, one is Weber per meter square or Tesla. So just remember the all units. So units also I will ask in exam. So yeah, you are going to strip test, right? So in that strip test, I'm going to ask that what is the units of flux density, what is the units of flux intensity. You should aware about what are the units of all parameters. So by using this equation, we go for finding. We have to find that what is the value of flux density, that is Bx. So if you want to take time, just say why, because if you note on the equation, it will take time. See, after completion of class, you have to send your what you note down the all equation. You have to send to me. Then only you will get the attendance. Why? Because so simply saying that class and you are listening, it is not a good manner. You should have to note down the equation. Why? Because it is completely derivation part. Then only you can understand how the equation will come. Now, so until now we derived that flux density and flux intensity. Now we have to find out what is the flux will be generating in a particular area, and let us see how it will be calculated. For the element having the thickness dx, why? Because thickness also one of the parameter will make the flux generation of flux, and the thickness is dx. The flux will be product of bx and cross sectional area of the element normal to the flux lines. So this is the equation. We can this is the equation, that is the flux will generate the in a conductor, and it is equal to product of flux density into cross sectional area into dx. So here cross sectional area is considering as a 1 meter. So if the axial length of conductor is 1 meter, then flux per meter of the length is given by. So here I am considering that axial length is 1 meter. Then the d pi is equal to bx into 1 into dx. This is the equation. Now from the equation 7, what you have to modify this equation means just substitute the bx value here. That is mu x in divided by 2 pi r square into I into 1 into dx. From this equation, finally d pi equal to nu into ix divided by 2 pi r square into dx. So it is a 1 meter for the axial length of the conductor. Just note down these two equations, and the reference it is equation 8.